So I suppose I'm going to begin. My name is Christopher Leach. I'm here at Open Daylight with Yale's network team to talk about Magellan, an automatic SDN pipeline solution for pipelining oblivious Open Daylight programs. In recent years, multi-table pipelining has increasingly become a basic paradigm for routers. Most modern routers implement flow tables as a deck of flow tables triggered by packet attributes, such that a packet is entered into the first flow table. The flow table performs an operation on a lookup on that packet, stores metadata, and as the packet progresses through this deck of flow tables, the packet, the router comes to a conclusion based on the metadata generated by the flow tables and the flow tables' reaction to the packet themselves. This, however, leads to the packet realization problem. That is, given a given control policy, a given program that we'd like to implement on our switch, and the current state of the network, how to generate a pipeline design satisfying the pipeline constraints, such as maximum pipeline size, such as memory in any one table, and populate the content of that pipeline. This problem is especially taxing, I suppose, because of the fact that there can be many individual pipeline switches that one might want to put an algorithmic policy on, and it's a waste of programming time for one to implement one's pipeline on one's control policy on every single individual pipeline individually. What Magellan attempts to do is allow you to implement a given control policy and a given state on any type of switch you want completely homogenously, such that the programmer can use the abstraction of the switch as a discrete entity and be freed from the need to consider precisely how to lay out his policy and state across the range of pipeline topologies existent on the market today. Why is good multi-table pipelining important? Consider this program above, which is a really, really simple version of group-based policy. What happens is that on packet in, we examine the packet source and come up with a series of source conditions. We examine the packet destination and generate a condition set of destination conditions. And then if we can find source conditions and destination conditions, and the packet passes the contract specified by the source conditions and destination conditions, we forward to output 1. Otherwise, we drop the packet. We further assume that there are n hosts in our host table. Now, how can we do this? A naive implementation would be to turn the entire policy into a single lookup table. Such a lookup table would have n copies of the source hosts, and for each of those hosts, we need to compare it with all n of the destination hosts, such that in a one-table design, we require n² entries. However, there are better paradigms. A more efficient pipeline might be 2 tables. If we assume that there are k condition possibilities for the source table, and we assign each of those k possibilities an ID that we can trigger on the second table's lookup, then we can get the first table in n entries, mapping each source that has an entry to a lookup table, to a condition ID exactly, and otherwise dropping it. And then we can then take that condition ID and the destination port and map it to an action. This gives us a total of n entries for the first table and k times n entries for the second table. Provided that k is smaller than n, however, there exists a third obvious better paradigm. If we use 3 tables, the first 2 tables mapping source and destination switch to a particular to acquire the metadata. The first 2 tables mapping source and destination to a particular ID of condition set in the metadata, and then the third table mapping these 2 condition IDs to produce an action. We can simplify our tables down to 2n plus k² entries. N for the first 2, since we need to consider all n hosts in our host table, and k² in the third table, since we're merely matching each of our source conditions with each of our destination conditions. Provided that n and k are reasonably big, suppose that n is 4,000 and k is 100, the first paradigm requires 16 million rules. The second paradigm requires 404,000 rules, and the third paradigm requires just 18,000 rules. That is, good flow difference can make an order, good flow pipelining, good table layout can result in a difference of over 10 to the 3 orders of magnitude on a 6-line program when implemented on a commercial stock router. So, the takeaway, for the same program and state, different pipelines can have large differences in the consumption of switch lookup memory, which is the key resource in packet switching. So, why is this problem hard? Table population is not at all obvious. It's probably hard for many. Even if I was to give you the table layout, physically being able to look at every possible combination of each of the tables and physically implementing the lookup table, especially on hard and non-intuitive programs such as group-based policy, is very much non-trivial, to the extent that it may be unrealistic to expect the average program to implement such design. Actually getting the table layout is even harder, since good pipeline design involves global optimization across the whole program. This is a not at all intuitive thing. Suppose that most programs consists of a series of discrete policy ideas, which are intuitively programmed in discrete chunks. Consider the program above. At a high level, the program looks to see whether the packet satisfies a simple group-based policy. If it does, it forwards it. Otherwise, it drops it. This program is most intuitively written in 2 distinct modules. The first module, the module above, simple group-based policy, determining whether or not a packet satisfies the group-based policy's contract, and the second policy dealing with the nuts and bolts of routing themselves. A naive implementation of this might be to use 6 different pipelines, 6 different lookup tables, all in a pipeline, the first 3 handling the first module in a program, and the second 3 handling the second routing module in the program. However, an optimal solution is obviously to use just 3 tables, since we can combine several of the different tables in each different module into a single coherent whole. To be able to arrive at this optimal solution requires the weaving of different policies together, of different policies' logic into a single coherent whole, which is a highly non-trivial optimization on any program of sufficient size. Takeaway: simple local composition can use a lot more tables than a global design can. Now that we've established what the problem is, and now I've hoped we've established why it's hard, I'd like to talk about how Magellan attempts to circumvent and solve this problem. We have 2 basic insights. The first basic insight is that we can think of a function as consisting of a series of instructions. Each instruction is a table, a mapping from a series of input variable states to a series of output variable states. For example, we can take our familiar group-based policy and we can deconstruct it into a series of 5 tables. The first table mapping packet.source to its condition set. The second table mapping packet.destination to its condition set. The third as a branch between 2 tables, which serves to break up the table flow, which takes in the source condition set and the destination condition set and sends it out to 2 different tables. And the 4th and 5th tables simply being 1-line tables which return a specific action when reached. Once we've turned our policy into a set of instructions, we can then actually lay out these instructions as tables. Table number 1 takes all possible Ethernet sources and turns them into source conditions. Table 2 taking all possible packet destinations and turning them into source conditions. Table 3 taking every single permutation of these conditions and mapping that to a jump to a different table, so on and so forth. How do we do this? First of all, we replace every if statement in the program by assigning its Boolean expression to a guard variable, and then appending a dependency to that variable to any statement within the if statement. In the example above, for example, we take a given source and a given that takes a given source and a given destination, returns an algorithm if neither of them are null, and drops the packet if they are. We can map that into guard, which represents the Boolean expression calculated in the if statement, and then leave a dependency on guard in the two instruction tables that represent returning the result of the algorithm and returning dropping the packet. Our second step is replacing all loops with black boxes. Loops beyond a very, very simple set of loops can rapidly lead to non-Turing complete or very, very long pipeline programs. Being able to optimally map a program with a series of loops to a lookup table is equivalent to solving the halting problem. It cannot be done. And thus, we take the trace of each loop and we turn that into a function itself. So, the way we take the trace of this loop is that every variable outside the code block that the block is dependent on is an input to this code block, and every assigned variable inside the code block is an output. In the example we see on the second half of the screen, we have a loop which is dependent on source switch and the number and a set of block switches, and puts out root, a variable, as either true or false. This loop would be turned into a trace, an instruction, a black box, which takes in source switch and block switches, the two variables outside the loop is dependent on as inputs, and produce reroute, the only instruction that the loop modifies, as an output. Thirdly, we remove every variable declaration from the program, and we store all such declared variables in a symbol table, which we will then populate over time. Fourthly and finally, all remaining statements are now assignment statements. We convert all variables to single assignment. That is, if we have the program a equals 1 and then a equals a plus 1, we convert the first a we convert the two instance assignments of a into discrete variables. We call one a0, call the second one a1, and we modify our program instruction tables representing these two instructions accordingly. Since variables are assigned only once, the graph that we get once we've converted all instructions to tables is acyclic in terms of dependencies. That is, there exists no cycle of graphs where each edge in that cycle is a dependency of one instruction table on another instruction table. Problems. PIT is not a solution in and of itself. First, it can still generate very, very large table size. A naive construction of each instruction table is still not practical. A hypothetical single function which takes in 10 variables still produces domain of the first variable times the domain of the second variable, all the way over to the domain of the 10th variable rows, which is still far too large for many physical pipelines. Secondly, PIT can generate simply too many tables. A switching element only allows for a small number of flow tables, and a program can have many, many, many instructions. For example, Cavium allows 12 tables for each for line card rate. That is, it's a pipeline of 12, and it can have an absolute maximum of 48 tables. Many programs that exist of any complexity such that you'd actually want to implement them obviously have far more than 48 different instructions. This leads to our second insight, table merging and compact mappability. Let's start with compact mappability first, which handles the too large table size problem. Consider instruction 1 that we've seen earlier. We map all 2 to the 48 possible Ethernet source ports, and we map them to a given source condition. Given that we may have a very small number of source conditions relative to 2 to the 48, one approach to solving the problem is only considering the n values in the host table that are actually necessary, not all 2 to the 48 potential packet source input values. The table size here trivially can be simplified to n plus 1, the n host table values, plus a default value that drops programs, not 2 to the 48. Table lookup is a key type of compact mappable instruction. That is, the ability to take a program with a huge domain and based on given table constraints, simplifying that domain down to a small series of variables is vitally important for representing functions in a way that can actually be fit onto genuine silicon. A second example of a compact mappable instruction. Take the Boolean expression packet.source equals packet.destination. The naive way of doing this would be to list all 2 to the 48 times 2 to the 48 different variables. If there wasn't, the obvious problem with this instruction is that there are not enough atoms in the universe to represent this particular pipeline. A more sensible solution might be to compare each individual bit in packet.source and packet.destination in the lookup table, making use of TCAM memories don't care bits, map every single circumstance where 2 bits in a given function disagree to false, and at lower priority to execute the if statement if none of the individual variables don't line up, mapping everything else to true, simplifying a 2 to the 98 row table down to just I suppose if each of the 40 down to a 97 row table. Second example of compact mappable statement. If we have a Boolean expression that we want to turn into a guard variable, rather than running through all 2 to the 48 entries, we can take a small subset of those entries where the solution is different from the general. We can map each of those specific cases to the specific result, and then we can let a default value, again placed at a lower priority of flow rule than the rest to act as an else statement, handle the remaining nearly 2 to the 48 cases. Our second insight, converting a PIT to pipeline, involves merging and rearranging them. This handles the fact that most programs produce far too many PIT tables for a given pipeline. Why is this hard? First of all, mapping something to an arbitrary pipeline topology adds huge number of constraints, such as the number of tables, or such as we can't have a table of such and such size on a particular stage of the pipeline. Secondly, there might be many, many tables within a PIT. And thirdly, combining 2 tables, one matching on attribute 1 and another on attribute 2, can lead to a combination explosion, precisely the difficulty that we set out to avoid when we broke the program down into PIT tables in the first place. One naive algorithm is just to consider the table layout problem as a graph partition problem, where the number of partitions is greater than the bound x, and then enumerate all possible partitions of the graph, and select the smallest solution feasible under hardware constraints. The obvious problem is that there are just too many possibilities to enumerate feasibly. There are a total of the number of partitions to the power of the number of individual tables, since each of the n types of tables can be put into each of the m different partitions. And that obviously explodes very, very quickly. Again, there are 3.8 times 10 to the 81 possible mappings from a program with just 50 intermediate variables to a Cavium's 48-stage pipeline. You'll notice this is the second case where there are not actually enough atoms in the universe to construct a router desirable for this solution. Not enough atoms in the universe to store all possible permutations of the solution. Thus, our algorithm involves PIT embedding using efficient tree recursion. This is a little bit of a complex algorithm, so I hope you'll bear with me. To start off with, we consider the dependency graph. That is, we split every single PIT table down to the point such that each PIT table only produces one output variable. We can trivially do this. If a PIT table produces 2 output variables, we can make 2 tables, both with the same input, and each with a single variable output. We label each of the PIT tables based on what the output variables are, and then we add another n nodes for each attribute we're given at the start of the program. That is, a node for each variable that we're given that isn't actually calculated in a PIT. Then we create a graph using the dependencies of each PIT. That is, if a given table takes as an input variable the variable output by another table, or the variable given by the packet, we take an edge from the table that generates the input to that particular PIT table. That is, in the program that we see up above, the variable A is dependent on the variables x and y. The PIT table that generates variable A takes as inputs x and y, and we create a dependency graph. Now, any node on our graph with no known ancestor is a node whose value of the variable is known, whether it's because we were given that variable as a starting variable or that we've already calculated it in some sequence of lookup tables that we've already established at some point in the tree recursion. This is trivially true, since recall that an arrow entering a particular node on a graph means that whatever at the end of that arrow is a variable that particular variable is dependent on. Now, we then consider each and every subset of nodes that have no ancestor and whom can create a node. That is, there exists at least one node whose parents are all in this subset. On the graph above, such subsets would be xy, which have the variable a as a child, yz, which have the variable b as a child, and xyz, which produce a and b. Notably, we do not consider subsets such as y, because y on its own cannot generate any single variable. We are now going to recurse on each of these subsets. We create a table which involves the subset's variables as an input. And if any of a given node's parents are in a subset, we add that variable to that table, and we remove all the nodes and coming edges, because that is, we're slowly building up a set of tables such that if a variable is created in that set of tables, that variable is not given a dependency on our graph. Our graph strictly shows dependencies which we have not accounted for. If a node has no children, it means it's useless. If a node has no children because of the fact that we're always following arrows down when we're calculating these tables, it has no parents. And if it has no children, no remaining variable in the graph is dependent on that variable, and therefore we can simply remove it from the graph. Now, for example, if we pick the set xy, as shown in the diagram, all of A's parents are in x and y, so we'd create a table which takes an x and y and spits out A. We'd remove we remove every single edge going into A, since we've already taken care of those dependencies in our list of tables. And x, which is disconnected from the main graph, is entirely removed to give us a new subset of input variables. If after finishing this process there are still nodes in the modified graph, it means on this particular branch there still are permutations of dependencies which are not accounted for. We cannot calculate every single variable in our graph using the tables at hand, and therefore we must recurse on that graph until we can. Otherwise, we now have a series of tables at the end of that particular branch of recursion. We estimate the table size, and we save that particular set of tables if it's the smallest calculated. Naturally, proper PIT embedding is an NP problem. Solving it there exists no solution that we know of in polynomial time. However, this approach stops the huge explosion of quadrillions and quadrillions of possible graphs on a realistically sized pipeline with realistically sized programs, because we constrain every set of tables that we look at to what's physically possible within the graph. What's physically possible given a particular program's dependency list. Finally, we have to estimate the size of each subset of tables we generate. A naive way of estimating any table memory footprint is by taking the product of each input variable's cardinality, that is, by taking every single value that each input could possibly have, and then calculating its length, and then multiplying the result by the sum of the data length type. That is, in this particular table, we take every single value that P source could have, every single value that P desk could have, every single value that P input switch could have. We multiply them all together. This gives us the number of rows. And then we calculate the number of bits in each row. That is the sum of each of their data type lengths. And using this gives us the total table size, the total number of bits in silicon this table is going to take up. One optimization here. If we can find a surjective function between two table input variables, x and y, such as fx equals y, this tells us that y can only variable when x variables, because f, to be surjective, has to be a deterministic function. and we can leave out the cardinality of y when estimating product size. That is, if in-switch is some function of packet switch, which you can see above, we don't need to worry about in-switch's size when calculating the size of the table, because there will exist no points at which in-switch varies and the source switch does not. So, to conclude, how does Magellan work? We take a particular series of algorithmic policies, we compile it down to an intermediate representation, in this case, a series of per instruction tables. We then lay out the pipeline size via smart recursion through every possible combination of these per instruction tables. We then generate these tables in Silicon and populate them. We add a punt handler. That is, if there exists a particular location in this code that we cannot turn into Silicon, we send that back to a central controller. And then finally, we take these rules and we give them to Open Daylight, and Open Daylight implements these rules as open flow tables on switches. Briefly, because I know we're running out of time, a demo. Is this going to work? Yes, it's going to work. Superb. Okay, so consider the processing logic of a standard inter-domain ingress router. This router has multiple peering routers and needs to process each received through a sequence of policies, which represent a discrete networking concern and all logically disjunct. Economic routing, according to economic policies, such as no routing valley, wide area network optimization. Security routing according to security policies. App-aware routing that differs depending on whether the particular purpose of the routing is routing SSH, or HTTP or FTP packets, and so forth. Our particular program has 3 separate modules representing 3 different algorithmic policies, which will weave into a coherent, optimized whole. The first, no valley, we check to make sure that we do no valley tracking and we drop our valley traffic. That is, we start out by finding the source internet service provider and the destination internet service provider. We make sure we know what these 2 internet service providers are. If we can't find them, we drop the packet. We make sure that if the packet is coming in from a peer, it can't go up to a provider. If it is, we drop the packet. We make sure that if it's coming from a provider, it does not then go on to another provider or another peer, unless there are special arrangements. We avoid valley traffic unless otherwise noticed. That is, we check if the source ISP is a provider. If it is, we make sure that the destination ISP is neither a provider or a peer, or if it is, we make sure that it's routed specially. Otherwise, we drop the packet. Second discrete policy, the to-customer module. If the packet is going to a customer, we pick an economic outcome for the customer. That is, we determine what the cheapest internet service provider is, and we calculate a route by acting on that destination input internet service provider. The final independent module handles security concerns from what the customer is trying to do. If the packet comes from a customer, and for example, unless it's an SSH, we drop the packet from security returns. For security concerns, we check the packet's ingress port, and if it's not, packet 22, and if either the packet's source comes, and if the packet source comes from a customer, and if the packet's destination is to a provider, we drop the packet. Now, suppose that we want to weave these 3 very different policies into a series of just 3 tables. We run the program, we compile the program, and perfect. We find that the optimal packet layout is a table which takes in the source destination and maps it to the source internet provider, a table which takes in the ingress port and maps it to a guard variable, and finally a table which takes all the metadata we've calculated and the remaining packet attributes and uses this to come up with an action. Why is this approach effective? First of all, it might well be, in this particular case, the number of possible packet destinations was large compared to the number of internet source providers, and we optimized the third table by using the smaller internet source provider as a stand-in for considering every combination of input source and output source. And the second table provides the optimization of, instead of having a packet ingress port, which is 48 bits on each row of this huge table, we replace it with a guard variable, which consists of a single bit. Suppose now KVM offers us a two-table router. This requires a totally different pipeline output, and without Magellan, you'd have to sit down and re-optimize the entire thing, which is already something that a programmer might have a difficult time doing. With Magellan, on the other hand, recalculating this program for that separate packet is as simple as pushing a button. And when we do so, perfect. We get an optimal two-table lookup. Note that we're combining a huge number of concerns here into a single else statement. That is, every single example where you'd want to drop it, unless we know what the destination is and we know what the ingress port is. That is, unless the drop function comes from that very last policy where we dropped it if packet source was 22 and it was going to a customer. Everything else we simplify into a single drop state. And again, we can do this if we say want 5 tables. We can run Magellan. And for this particular outcome, Magellan will spit out the correct answer. You'll notice here that Magellan only spits out 3 tables, by which we mean that Magellan sees no purpose in adding extra tables to our pipeline. Magellan looks through every possible table that could possibly fit our pipeline, regardless of whether that table uses all of its resources, and only spits out a solution which may not use up the entire topology, but it is the optimal solution for that particular program topology. So, to sum up, because it's late, I know that we all want to go home. This is no good. And I think I know what to do. We need to go to the summary slide, and we need to hit play from current slide. Perfection. Okay. As you see, multi-table pipelining is crucial for flow table scalability, which is why the general progress of pipeline solutions has been in that direction. See KVM, P4, Marvel, and so forth. But at the same time, actually programming for multi-table pipelining adds substantial programming complexity. Magellan provides the first tool which automatically generates both table design and layout for arbitrary programs written in natural-to-program high-level languages. Our system is currently in beta, and we hope to create a solution which sits on top of OpenDaylight as a driver, which compiles arbitrary programs into OpenDaylight and uses OpenDaylight to incentivize the creation of a switch layout for a system using the generated series of float tables. Thank you very much for your time. This problem is especially taxing, I suppose, because of the fact that there can be many individual pipeline switches that one might want to put an algorithmic policy on. And it's a waste of programming time for one to implement one's pipeline on one's control policy on every single individual pipeline individually. What Magellan attempts to do is allow you to implement a given control policy and a given state on any type of switch you want completely homogenously, such that the programmer can use the abstraction of the switch as a discrete entity and be freed from the need to consider the flow table performs an operation on a lookup on that packet, stores metadata, and as the packet progresses through the stack of flow tables, the router comes to a conclusion based on the metadata generated by the flow tables and the flow tables' reaction to the packet themselves. This, however, leads to the packet realization problem. That is, given a given control policy, a given program that we'd like to implement on our switch, and the current state of the network, how to generate a pipeline design satisfying the pipeline constraints, such as maximum pipeline size, such as memory in any one table, and populate the content of that pipeline. So I suppose I'm going to begin. My name is Christopher Leet. I'm here at Open Daylight with Yale's network team to talk about Magellan, an automatic SDN pipeline solution for pipelining oblivious Open Daylight programs. In recent years, multi-table pipelining has increasingly become a basic paradigm for routers. Most modern routers implement flow tables as a deck of flow tables triggered by packet attributes, such that a packet is entered into the first flow table, precisely how to lay out his policy and state across the range of pipeline topologies existent on the market today. Why is good multi-table pipelining important? Consider this program above, which is a really simple version of group-based policy. What happens is that on packet in, we examine the packet source and come up with a series of source conditions. We examine the packet destination and generate a condition set of destination conditions. And then if we can find source conditions and destination conditions, and the packet passes the contract specified by the source conditions and destination conditions, we forward to output 1. Otherwise, we drop the packet. We further assume that there are n hosts in our host table. Now, how can we do this? A naive implementation would be to turn the entire policy into a single lookup table. Such a lookup table would have n copies of the source hosts, and for each of those hosts, we need to compare it with all n of the destination hosts, such that in a one-table design, we require n² entries. However, there are better paradigms. A more efficient pipeline might be 2 tables. If we assume that there are k condition possibilities for the source table, and we assign each of those k possibilities